All right, in chapter 3, we talk about determinants. So we start off with an intro, where we would naturally start off. So 3.1, Intro to Determinants. Now, we've touched a little bit on determinants already, so we have some idea of what we're headed for, or what we're talking about. So, we had a 2 by 2 matrix, A, B, C, D, and we talked about how the determinant of that would be AD minus BC, and how a matrix is only invertible if its determinant is not 0. So if you get a determinant of 0, you know you have a non-invertible matrix, okay? Now, let's also establish some notation here. When we're talking about the determinant, we're going to use these vertical bars like absolute value, okay? Now, I want to be clear that determinant is not the absolute value of a matrix, okay? It is a important quantity that maybe bears some relationships to something like absolute value, but determinants can be positive or negative. They can be 0. Absolute values can't be negative. So it's not a absolute value, but it does have some similarities, okay? And especially in the notation. The notational similarity is obvious with the vertical bars, okay? So if we write this with the brackets, that is the matrix, and we might talk about its determinant, but those vertical bars also mean the determinant. So if I have, A is equal to this matrix, this notation with the vertical bars means the same thing as the determinant of A, and we abbreviate determinant DET. So determinant of A. And we know how to find the determinant. Let's just do a quick refresher with a simple matrix: 3, -1, 4, 7. So remember AD minus BC, so the determinant here, let's call this matrix B. So the determinant of B, all right, would be 3 times 7, which is 21, minus 1 times a -4, or -1 times 4 is -4. So I wind up adding, I get 25 for the determinant there of that simple matrix, okay? So we should remember how to take the determinant. We know that this is invertible because the determinant's not 0. We know these columns are independent as well, and if you have all independent columns, we know by the invertible matrix theorem that gets us a square matrix. We know the rank of B is 2, right? We know all these different things together as well to refresh our memory, okay? But we only have that easy setup for a 2 by 2 matrix, okay? So we want to use that then to figure out, okay, what else can I deal with, okay? So let's start with looking at a 3 by 3, because we want to expand our definition here to more challenging, more interesting, more difficult matrices, okay? So A, B, C, D, E, F, G, H, I, okay? I got my matrix there. Now, we could imagine doing row operations on this matrix. I would wind up with A, and I would get zeros below it, right? We're familiar with those row operations. Now, I'm not going to write out the whole gist of this setup, but I can clearly see I get A with zeros below it, okay? And then I would have some sort of 2 by 2 sort of piece of the matrix there that I'm going to emphasize, okay? So you think about what these pieces would be, okay? I would wind up doing A times a -D to get this where this would cancel out. Okay, I would do an appropriate row operation, get that to add up to 0, do an appropriate row operation, get that to add up to 0, and that would modify these accordingly, right? BE, GH, things like that, okay? All right, and then there would be still B and C along this top row, okay? So as I look at this piece here is a 2 by 2 matrix, okay? So I can just look at that 2 by 2 matrix now and say, okay, I can make some observations about this. Notice this is A, it's still unchanged, okay? So what I'm going to do is what's called a cofactor expansion, okay? And in a cofactor expansion, you ignore the other points in that row and in that column. So here for my A, I'm going to ignore the D and the G below it and the B and the C to the right of it. And then I'm going to take this 2 by 2 matrix here in the lower right, okay? So my determinant, so we're going to call this matrix A, naturally. So the determinant then of A, what we're going to do is we're going to take little a, multiply it by the determinant of E, F, H, I as a 2 by 2 matrix. We know how to do the 2 by 2, so we can do that there, okay? Then I'm going to shift over to the next point. The next point would have B, and I would ignore, again, the column and the row that it's in. So ignore the column and the row. Okay, so I'm going to have, my next one is going to have DG, because those are the numbers here, and then FI. Okay, and again, absolute value bars because I'm talking about the determinant, and that's going to get multiplied by the number at the top, which is B. Now, if we think about what we did for 2x2 matrices, right? When I went to that second spot here and came across this way, it was negative, right? It was positive on the main diagonal, negative on the off diagonal. Well, the same idea is going to happen here. As I move over, it's going to go to a negative. And then when I move over again, it's going to go back to positive, okay? And so then my last one here, I'm going to have C. And again, I'm going to ignore the column and row that C is in. And that's going to leave me with DEGH. So DEGH. Okay, and now I have 3 2x2 matrices that I can easily take the determinants of. Okay, so I've got a nice, relatively easy setup that I can deal with here. Okay. Now we can also apply this cofactor expansion idea to any column or row. Okay, so I took ABC, the top row. I could have done DG, ADG, BEH. We can do any of those types of operations. And depending on the matrix, we'll see why that can be useful, okay? So we'll work through that going forward here. So first, let's take a new matrix here. Let's call it A again. Sorry, I lack creativity in my matrix naming. 2, -1, 3, 4, 1, 1, and 0, -3, 0. Okay, and we're going to look at its determinant. Okay, so I'm going to do the cofactor expansion here. That's what this is called. This is called cofactor expansion. Okay, because I'm taking the smaller piece of a matrix, the smaller partition, and multiplying by its cofactor that is outside of that smaller piece. Okay, so upper left now is 2. Ignore the row and column. So I'm going to have 2 times the determinant of, in this case, it's 1, 1, -3, and 0. Okay, ignore the column and the row where the 2 is located. Then we go minus. Okay, it's minus a -1. Be very careful about your signs, S-I-G-N, positive negatives, and keeping those straight. Make sure you take care of those and you're careful. Okay, so ignore the row and column that it's in. I'm left with 4, 0, 1, 0. 4, 0, 1, 0. Okay, and then the third spot here is going to have 3. Again, ignore the column and the row that it's in. I'm left with 4, 1, 0, -3. Okay, 4, 1, 0, -3. Okay, and now I could write this out kind of term by term here. This is going to be 2 times, this is 1 times 0, 1 times 0, minus, because the determinant, 1 times -3. Okay, I'm being very deliberate here in writing out all the little pieces. You could obviously do this in a few fewer steps than this. Then I would go to +1, and this would be 4 times 0 minus 0 times 1. That'll be real easy when we simplify. Plus, and I have 3. Again, I put the plus here because it was minus and minus. Negative, negative makes positive. And then I'm going to have 4 times a -3 minus 1 times 0. Okay, and now we simplify. So I've got 2 times 0 plus 3, so 2 times 3, plus 1 times 0 is 0, plus this is going to be 3 times a -12 minus 0, so 3 times a -12. So I have 6 minus 36, so my determinant is a -30. Done. And I talked about how I could use any row and any column, okay, in order to find that expansion, okay? So if I look at my matrix A here, well, row 3 has 2 zeros in it, okay? So let's use the third row for my cofactor expansion. Now we have to be careful because there's a sign chart here that takes that's important when we're using this cofactor expansion. So I'm going to show you how the book represents it because it'll be faster than me writing it out, just to be totally honest. Okay, and you see it's this alternating plus minus situation. So plus minus, plus minus, plus minus, plus minus. That continues indefinitely. Now you can see the 3x3 grid set up here. Okay, this also looks like a lot like Descartes' rule of signs, if you're familiar with that from algebra and pre-calculus. If you're not, then don't worry about it. Forget I ever said it. It's not a big deal here. Okay, so this is going to be plus minus plus. Okay, so I could also find the determinant of A by doing 0. Okay, again, ignore the row and column that it's in, so I get this upper corner. So 0 times -1, 3, 1, 1, minus, again, because it's going to be plus minus plus, so it's plus minus plus going along the bottom. Okay, it's going to be -3 times, ignore the column and row that it's in, so you get 2, 4, and 3, 1. 2, 4, 3, 1. And then that's going to be plus 0 times, ignore the column and row, so you get 2, -1, 4, 1. 2, -1, 4, 1. Sorry, I ran out of room there. But we can squeeze it in because these are multiplied by 0. They have 0 outside. So I know that each of those goes to 0. And let me represent it with a little arrow there. So I really just have this middle one, which is going to be 3 times the determinant of 2, 3, 4, 1. Okay, and so on the inside here, I'm going to have 3 times 2 minus 12. That's 3 times a -10. That's a -30, just like before. Okay, so great news there. So you can use any combination of rows or columns to facilitate slightly easier computations. Okay, so for B now, in fact, let me just write it in determinant notation here. I'm going to have 2, 1, 1 on the top row, 0, -1, 1 on the middle row, and -2, 4, 7 on the bottom row. Okay. And I want to find the determinant of this. Well, my middle row here in particular has a 0 in it. So that's going to make for the easiest computations. Okay, remember plus in the upper left. So we go plus minus plus, minus plus minus, right? It goes plus minus plus going down as well. So if I'm going to do the determinant, I'm going to do it from the middle row, a cofactor expansion of row 2. So I would get minus 0. Again, I get minus from the signs in the cofactor expansion. Times, ignore the column and row that it's in, so I get 1, 1, 4, 7, 1, 1, 4, 7, plus, second coordinate here is -1. Again, ignore the column and row, so I get 2, -2, 1, 7. 2, -2, 1, 7. And then the last one, this is going to be minus, third coordinate here is 1, times the determinant. Again, ignore the column and row. So I get 2, 1, -2, 4. 2, 1, -2, 4. Okay. So this is 0. 0 times anything is going to be 0. Okay. So I've got -1 times 2 times 7 is 14 minus a -2. Okay. Be very careful with your positive and negative signs. It's easy to get crossed up. Okay, minus 1, and then this one is going to be 2 times 4 is 8, minus a -2. So let's figure out what we have here. I have 14 plus 2. I have 16, but it's negative. Okay, I have negative, and then this is 8 plus 2, so it's 10. And add those together, and I get a -26. And there is my determinant. Okay, so computing determinants is not too difficult. Okay, and we also know this gives us a lot of things for the invertible matrix theorem. Okay, remember, a matrix is invertible if its determinant's not 0. So neither of these determinants, for example, were 0. That means that the matrix is invertible, means the columns are independent, means the rank is equal to n, which is 3. The dimension of the null space is 0. Linear transformation with this matrix is 1 to 1 and on 2. All those things, all those 18 things we get from the invertible matrix theorem, okay, they all go in from this. We can build it on this idea, okay? All right, now the next thing we want to notice or we want to use is what if I have a triangular matrix? Okay, so triangular matrices have been very important all along the way. We've had several examples with one. Okay, so let's say 2, -3, 1 with 4, -1, and 16, and then zeros below so that I get a triangular 3 by 3 matrix. Okay, what you should notice here is if you do a cofactor expansion on this, go down the first column, because if I go down the first column, I'm going to get a number here, but then all zeros. Okay, maybe it's upper triangular, in which case go across the first row, because you're going to get, I'm sorry, maybe it's lower triangular. If your zeros are up here, go across the first row, you'll get a number and then zeros. Okay, so if I go for the determinant of this, I'm going to take cofactor expansion is going to be 2. Okay, again, ignore the row and column that it's in, times the matrix -3, 4, 0, 1, the determinant of that. And it would be -0 times some matrix, but who cares because it's times 0, plus 0 times, again, some matrix, but who cares because it's 0. Okay, so both of these go to 0. And you see the only one we care about is here at the front. So I have 2 times a -3 minus 0. So I got a -6. Okay, now what you should notice is if I have a triangular matrix, I'm always going to kill off all these other rows, all these other terms. Okay, I'm going to get 0 times a matrix. That's not important, okay, because 0 times anything is going to kill it off. So I'm going to get this upper left point 2. Then I'm going to get the rest of it here, which, if I look here, all I did was multiply here because there has to be a 0 in this other spot to make the reverse diagonal 0. So we have a theorem, this is theorem 2 for chapter 3, that says if you have a diagonal matrix, I'm sorry, not a diagonal matrix, a triangular matrix. So if A is a triangular matrix, then the determinant of A is the product, right, multiplication, product, of the entries on the main diagonal. Okay, if A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal. And that carries over for any size matrix. I can expand this out to 4, 5, so forth. Okay. Now, there's another method for determining the determinant, for finding the determinant. Okay. It doesn't really have a cool name. It's just another common method, especially for a 3 by 3 matrix. So if I have a 3 by 3 matrix here, I'm going to show you -3, 4, 1, 2, 6, -3, 0, 2, 1. Okay. Now, whether this is easier or harder is kind of in the eye of the beholder. Okay. Well, think about what we did for a 2 by 2. We multiplied down the main diagonal. Okay. Multiply down the main diagonal. Well, I go down this diagonal. If I go to the next diagonal, I kind of run out of space. I don't have a third thing here to multiply. Okay, so we're going to copy a version of the first column. So -3, 2, 0, I just copy here on the outside. And then if I go to the third one, I'm going to need 2 rows, 2 columns to do that. So 4, 6, 2 in the second. So what I'm going to do is I'm going to multiply down these diagonals. Okay, each one of those is going to be positive. And then I'm going to come back the other way, just like I did for a 2 by 2. Okay, so I'm going to multiply on the diagonals and then subtract on the backward diagonals. Okay, so down this main one here, my determinant, I'm going to have -3 times 6 times 1. Second column, second position here, 4, -3, 0. 4, -3, 0. Okay, plus again, 1, 2, and 2. 1, 2, 2. Okay, so those were the main diagonals. Now I'm going to subtract going the other direction. So 1, 6, 0. 1, 6, 0. And again, I'm showing all the steps. You could do some of these a little quicker, especially with the multiply by 0. -3, -3, and 2. Okay, so it's minus because I'm doing the determinant and going backwards. So -3, -3, +2. And then backward again. So I've got 4, 2, and 1. Minus 4, 2, and 1. Okay, now I can add up those numbers. So -18 plus 0 plus 4 minus 0 minus, minus, and minus. So this is going to be -9 times 2, -18 minus 8. Okay, I put all those together. I've got -18. Then I'll have -14. -14 and -18 makes -32. And -8 is going to be -40. Okay. Now we're going to talk about a couple more types of matrices here and things that we do with determinants. Okay. So one type of matrix I have is called an elementary matrix. Okay. And an elementary matrix differs from the identity matrix by exactly one row operation. Okay, so if I take a matrix here, this is the identity. Okay, so imagine the row operations you could do here. I could switch two rows. So let's switch the first and second rows. So I get 0, 1, 0, and 1, 0, 0, and 0, 0, 1. Okay, so I could do that. That's an example of an elementary matrix. I could scale one of the rows. Maybe I do 2, 0, 0, 0, 1, 1, and 0, I'm sorry, 0, 0, 1, 0, and 0, 0, 1. I merged rows 2 and 3 together there and almost did mess it up, not almost. Okay, I could just scale row 1 and I'm back to the identity. Okay, I could also do a replacement operation, right? I could say take 2 copies of row 1 and add it to row 2, and I would get something like 1, 0, 0, 2, 1, 0, 0, 0, 1. Okay, it just takes the one row operation to fix this. Now, the important thing to notice here is for any elementary matrix, because there's just going to be one row operation different, I'm either a triangular matrix, like this one, or if I'm not a triangular matrix, I can switch to being one. Okay? Here, this matrix is not triangular, but if I switch rows 1 and 2, I'm back to a triangular matrix. Okay? So let's look at these examples and figure out what happens to the determinant of an elementary matrix. Okay? So if I look here, this is my identity. The determinant of the identity is clearly 1. Okay? You multiply down the diagonal ones, even if I head all the way to 4, 5, whatever, diagonal ones, all ones, you come back the other way, you're going to get all zeros, 1 plus 0, 0, 0, minus 0. So the determinant of the identity is always 1. Okay? If I go down here to this one, this is a triangular. So I know I can use my theorem that says that the determinant is the product of the diagonal. So the determinant of my matrix here, I'll call this matrix A. The determinant of A is going to be 2, the product of the diagonal. Okay, let's call this one B. It's maybe the trickiest one to see. Okay, so if I go to B, look here, let's do a cofactor expansion because I have all these zeros. So I have 0. This is going to be minus 1. And then my ignore the column and ignore the row. So I'm going to get 1, 0, 0, 1. Okay, so the determinant of B is going to be minus 1 times the determinant of the identity matrix. So that's going to be just -1. Okay, and then my one with replacement here, this is triangular, so we'll call this C. So the determinant of C, it's a triangular matrix, multiply on the diagonal, 1 times 1 times 1, all ones. So let's compare what happened here. When I did replacement, the determinant didn't change. Okay? When I scaled a row here to get A, I multiplied a row by 2. The determinant changed by the same scale. And when I did a interchange, when I switched 2 rows, the determinant became negative. Okay? So we have 3 properties here for determinants as they relate to row operations. Okay? And those 3 properties are, as they relate to row operations, so given the determinant of A is equal to K, if replacement is done, the determinant of the new matrix B will still equal K. If interchange is done, then the determinant of the new matrix B will be negative K. And if scaling is done, by a factor C, then the determinant of B will be equal to that factor times K. Okay, so if you scale, you simply multiply that by that factor. If you interchange, you make it negative, you switch the sign. And if you do replacement, then you leave that determinant the same. So let's take a look at an arbitrary matrix here. If I have A, B, C, D, E, F, G, H, I, okay, I'm going to do a row operation here, where I'm going to have D, E, F, A, B, C, G, H, I. So what's happened here is there has been an interchange. So if the determinant of A is equal to 7, then the determinant of my new matrix B would be negative 7. Okay, because I did one interchange operation. I switched row 1 and 2. So that's going to flip the sign to be negative. Okay. And remember that all these determinants fit in with these same properties, these same techniques, independence, so forth. Okay. All right. Now I want to do one more, a little bit longer example here with determinants. So hopefully you're kind of getting the hang of things. And then that'll be the end of our 3.1 video. And we will go to 3.2 next, which is going to be properties of determinants. Okay. So one more example. Bit of a longer example that you can think about how these apply to larger matrices. Okay, because we just use the same techniques generalized. I'm going to have 5, negative 7, 2, 2, 0, 3, 0, negative 4, negative 5, negative 8, 0, and 3, 0, 5, 0, and negative 6. Okay, and I just have the straight bars there. I'm trying to find the determinant. So take a look at your matrix here. One row or column is going to be much easier to use the cofactors for. So again, see where all the zeros are. They're all here in column 3. Okay, so I'm going to use column 3 to determine my cofactor expansion. Okay, so again, you ignore the row and column. Okay, remember how the chart goes here. It's plus, minus, then it goes down, minus, plus, minus. Okay, so my cofactor expansion, I'm going to have 2, this top entry, and then I'm going to have the determinant of this 3 by 3 matrix. So this 3 by 3 matrix is 0, 3, negative 4, again, skipping over the column, negative 5, negative 8, and 3. And then on the bottom row, I'm going to have 0, 5, negative 6. Okay, again, because I'm ignoring this row and column. Okay. Now, all of the other cofactors, all the other expansion terms are just going to be 0, because it's going to be 0 times a 3 by 3, 0 times a 3 by 3, 0 times a 3 by 3. So by picking the right cofactor expansion here, we've made things much easier for ourselves, because now I have another matrix that has a column with 2 zeros in it. Okay, so I'm going to just leave off the minus 0. We know we subtracted 0. It's still the same thing. Okay, now I'm going to have this 2 that's in the very front. I'm going to make a big bracket to emphasize that it's separate, so I'll take care of it at the end. Now I'm going to do the cofactor expansion with this first column. So I'm going to have 0 times a 2 by 2 matrix. Remember, it's going to go plus, minus, plus going down. Negative, a negative 5. Again, ignore the row and column that it's in. So the matrix here is going to be 3, negative 4, 5, negative 6. Okay, ignoring the row and column, 3, negative 4, 5, negative 6. And then it's going to be plus 0 times a 2 by 2 matrix. Okay, and I don't need to write down those 2 by 2 matrices because I know they are going to go to 0. Okay, so let's put these together. Negative and negative is going to be a positive, and 2 and 5 is going to make 10. So I'm going to have 10 times, and I'll just go ahead and write this matrix down one more time, because now I have reduced this, or simplified, or cofactored, or however you want to say it, this ugly 4 by 4 thing down to this relatively easy 2 by 2 determinant. Okay, so I'm going to have 10 times 3 times a negative 6 is a negative 18. Minus a negative 20. Okay, so plus 20. 20 minus 18 is going to be 2. So I've got 10 times 2. And the determinant of the whole matrix is 20. Okay. Now, if we go through and we copy the additional rows over here and go across there, that's going to be a lot of multiplying, a lot of places to make a mistake. Okay, going back, all the minuses, all the possible sign changes. If I go along the top row for the cofactor, I'm going to have some ugly 3 by 3s in here that are going to be challenging. Okay, so if I pick the right row and column, I can boil it down to being a much simpler operation. Okay, so that is cofactor expansion for determinants. That's also the sort of rule, shortcut, or cheat sheet for a 3 by 3 determinant. Okay. And we can work from there. Okay. Now, to give you an idea, for a computer, this cofactor expansion can be made very quickly. It can be automated very quickly with a good program. Okay. You know, the book gives a note about how, by today's standards, a 25 by 25 matrix is actually considered small. Okay, that's a relatively easy computation for the computer for it to work with. Okay, so you have few tools at your disposal, a few different things you can work with. Okay. Again, if you have any questions, please let me know. Okay, that should set you up for the 3.1 homework. We're really moving through things here pretty well. Chapter 3 is a pretty short chapter. There's just 3 sections, and section 3.3 is pretty light in particular. Okay, so we still have 3.2 is a little longer. 3.3 is pretty light. And that's the end of chapter 3. Chapter 3 is a very short chapter, just 3 sections. And then we will start talking about vector spaces in chapter 4. Okay? Again, if you need help, if there's something I can do for you, please let me know. Get in touch by email or visit the office hours time, and I'll be happy to assist you. Again, let me know how I can help, and I'll talk to you soon.